When last we met, we discussed the basic logic gates used in digital logic. Today we're going to talk about two other gates that are used. First off, the XOR gate. It has a symbol like this. Its state table is like so. This is an important gate for a variety of reasons. Number one, it is used in addition, which we'll get to in the next session. It is used for what's called parity, checking parity of a message to ensure there's no error in communication. And it can also be used to toggle inputs and toggle an input. In Boolean expressions, it is A, B. A with a plus with a circle around it is the symbol used in Boolean expressions for the XOR gate. Some simple identities that you might run into. X exclusive OR with 0 equals X. X exclusive OR with 1 is not X. X exclusive OR with itself is 0. And X exclusive OR with its complement is 1. What I was saying about toggling a input is shown with this one right here. If you have one input tied to 1, regardless of what input is on A, the inverse is going to be coming out the output. If you have a 0 on B, whatever's on A is going to be on the output. So you can selectively toggle whether or not a signal is inverted, which can be handy in mathematical operations. Looking at the way to implement a XOR gate, oops. It's a and OR gate. So it is either A inverted and B, or B inverted and A. That's the most straightforward way to implement a XOR gate. There's another way to do it, which we'll get into in digital logic class. Not as obvious, but it works as well. It's actually a little bit more efficient than this method. But this is the straightforward definition of it. It is A and A prime and B, or A and B prime. The stars are the and the plus is the or. The prime is the inverted version of the signal. All right. I guess I'm having to move fairly quickly through this. The XNOR gate, which doesn't get taught very often, is the inversion of the XOR gate. So it has the inversion bubble here on the output. And the state table is a 1 if the two inputs match. So the XNOR gate is sometimes called the equivalence gate, the equivalence operation. You could string these together and determine whether or not two binary numbers are equivalent in hardware without having to do software comparisons. But this can be implemented with a NOR gate and a AND gate. It is not often implemented in hardware, so you have to create it from other gates to get that functionality. Likewise, you could take an exclusive OR gate and run it through an inverter and have the same result. So you can get the equivalence operation and compare whether or not two bits have the same value. So moving on to universal gates. NAND gates and NOR gates are both universal gates because you can create an inverter from a NAND gate. You can create an AND gate from NAND gates, and an OR gate So the three basic components of digital logic, the inverter, the AND, and the OR can all be implemented using NAND gates. So all you actually need are NAND gates. You can implement any digital logic circuit using just NAND gates. Likewise, the NOR gate can be used to create an inverter. And an OR gate, and an AND gate. So a NOR gate could be used to implement any digital logic circuit that you want to create, because they are universal gates. You can use them for anything. Getting into NOR and NAND implementations is the subject of a section in digital logic, which we covered last week in the lecture. But yeah, it's the universal gates. You can go through the truth tables for each of these to verify the truth of this assertion. But like I said, I don't have a lot of battery on my recording device, so I went through this pretty quickly today. Monday, we will be having a quiz on digital logic, the various gates, the state tables, that sort of thing. In the meantime, have a wonderful day. See you next week.